Let me introduce you the idea of contravariance and covariance. So first I introduce you the idea of contravariance. So for doing that, let me draw a two-dimensional Cartesian coordinate system with x and y axis. So this is 1 unit, this is 2 unit, this is 3 unit, 4 unit, 5 unit in x axis. And let me draw a vector that is of 2 unit in length along the x-axis, and we can represent this this is x-axis, this is y-axis, and we can represent this 2 unit length vector as a column vector 2 0. So if we apply a scale transformation to the basis, that scales the basis to double of its original length, that is, this is 1 unit, this is 2 unit, and this is 3 unit. And this new our scale transformation transforms the 2 0 column vector to 1 0 column vector. So what we saw is, on scaling the basis up, or scaling the basis vectors up, uh, scales down the components, or results the scales down of the components of the vector. That's why 2 0 column vector transform to 1 0 column vector, so scales down the components of the vector. We know that the dot product preserves or conserves under coordinate transformations. So let me ask you, does our dot product changes the under this scaling transformation? Does it change? So let us check that. Before scaling transformations, we have the components of our vector as 2 0. For this 2 0 column vector, we need a 2 0 row vector to get the dot product value as 4. And this 2 0 row vector is called the dual vector, corresponding to 2 0 column vector. So to conserve, or to preserve the dot product value, or to preserve the magnitude of the dot product value, we need to change the components of the dual vector also for the scale transformations. Let us check that how these dual vector components change. For after scaling transformation, we have 1 0 as the column vector. For this we need a 4 0 dual vector. So we can see that the components of the dual vector, also the components of the dual vector scales up with the scaling up of the basis vectors. So this hence the dual vectors are covariant. Covariant means the dual vector components also scales up with the scaling up of the basis. So let us think how we can convert the covariant components to contravariant components. In the first case, we can use a 1-1 diagonal matrix to do that. But after the scale transformation, we need a 4-1 diagonal matrix to do that. To convert the contravariant components to covariant components, and these matrices are called the metric tensor of the coordinate system, or the metric tensor of the space. Metric tensor of the space. So from all this we can see that the magnitude of a vector, or the dot product of a vector with itself, is a covariant vector times a contravariant vector. And a covariant vector is equal to metric tensor times a contravariant vector. We can represent the covariant vector components with the symbol uh, x sub index mu, and this contravariant components with the x upper super index mu. So we can write the magnitude of a 4 vector x superscript mu. X superscript mu means the components of a 4 vector as the x subscript mu times x superscript mu, and also there's a summation there, summation sigma that running from mu is equal mu running from 1 to 4, and actually we don't need the summation there because we apply the Einstein convention here, so we automatically mean the summation there because there's a subscript mu and a superscript mu, so we automatically mean the summation there, and this is called the Einstein summation convention. I already talked that we can write a covariant vector as a metric tensor times a contravariant vector, and in 4 vector notation we can write it as this, and there's a summation over nu that running from 1 to 4, but in Einstein summation convention we don't need this summation symbol and there's automatically a summation there. So if we put back this equation in our dot product equation x sub mu x superscript mu, we get g sub mu nu x nu x mu. So in 4-dimensional Euclidean space, this metric tensor g sub mu nu is actually the identity matrix, the diagonal matrix 1 1 1 1 1. All other components are 0. But in Minkowski space is 4-dimensional, and this space is actually the space that we used in special theory of relativity, and in Minkowski space the first component of this matrix is -1, and this is actually the after effect of the constant speed of light. In some textbooks we also use the first component as +1 and the other 3 diagonal components as -1 also. So let me add an additional example for the covariant vector. We all know about the gradient of a scalar field phi, and we can take the gradient of a scalar field phi as del phi, which is equal to dou phi by dou x, which is the ith component, and the jth component as dou phi by dou y, and the kth component as dou phi by dou z. And you can see that if you scale the basis up, the x scales down due to the contravariance of the position vector. We already saw it, and if this x scales down, that implies the dou phi by dou x scales up because this x appears in the denominator of dou phi by dou x. And in summary, we can say that scaling basis up, the dou phi by dou x also scales up, and actually this is the covariance. And so we can say that the gradient of a scalar field and the gradient is covariant. So let us take the dot product in 3-dimensional spherical polar coordinate system to get an idea about the covariance, contravariance, and the metric tensor. So for doing that, let us take the square of a differential element dr square as a row vector dr d theta d phi times the diagonal matrix 1 r square sine square theta times a column vector dr d theta d phi, and this diagonal matrix correspond to this metric tensor x sub mu mu, and this as a whole correspond to this covariant vector, and this contravariant vector correspond to this.